So I'll say welcome to everybody and thanks for joining us today. This is our April meeting of the Science and Engineering Council. We're here online now for the time being still, and second Wednesday of the month. So happy to be at this, happy to be moving along with our programs in this forum. Just a quick note of who's from the board of directors here, Science Engineering Council, is myself, Tim Murphy, we got Cheryl Ebner, Yvonne DeGraw is with us, Bill Theringer, Bob Lilly, Gary Kravitz, and Steve Skopatz. That's who I see currently on the boards from our board. So here today, if there's anybody else, feel free to raise your hand and speak up. But so that's us. Again, every second Wednesday. Thanks to everybody who's made donations to this meeting or joined SEC and registered for this event. We have lots of ongoing, some are, it really helps with our administrative expenses. And also to our donations that where we help out with Science Fair Awards annually, which we did last month. Thanks for everybody joining on that one. And then also very importantly, we ask you to consider donating to our scholarship fund for the Santa Barbara Scholarship Foundation. Those scholarship fund donations are tax deductible. With that little bit of business, I think we can go ahead and turn this over to Yvonne to introduce our speaker today and also our upcoming meetings. So Yvonne, please take it away.
Great, thanks, Tim. Just a quick heads up about our next month's meeting. That'll be May 12th, and our speaker will be Dr. Danielle Tuma from UCSB's Bren School of Environmental Science. She'll be speaking on detecting the human fingerprint on wildfire and flood risks. That is, she'll be teasing out the contribution to extreme weather due to human-caused climate change. So we're looking forward to that. After that, our next meeting will be June 9th. So we'll be letting you know about our upcoming speakers and how to register by email. So make sure you're on our email list. Today, we're really happy to present this talk by Dr. Andy Howell, who's a staff scientist at the Las Cumbres Observatory and adjunct faculty in physics at UCSB. He is one of the most highly cited scientists in the world, according to Clarivate Analytics. Dr. Howell leads a team of more than 200 people studying explosive astrophysical phenomena in the global supernova project. They use dozens of telescopes, including remotely operated Las Cumbres telescopes around the world, the Hubble Space Telescope, and NASA's SWIFT satellite. Dr. Howell is also a TV host, appearing on shows including National Geographic, the Discovery Channel, the History Channel, and elsewhere. His YouTube channel, Science versus Cinema, investigates the science in movies. He's also a science advisor for movies, books, and TV shows. So we're pleased to have him here to speak to us today. If you have questions during today's talk, you can type them into Zoom's chat area during the talk, or you can ask them after the talk by unmuting yourselves. So Dr. Howell, go ahead. I think you're muted.
He's muted.
Okay, can you hear me now?
Yes.
Okay, great. Yeah, thanks for having me. Pleasure to speak to everyone virtually here. I'm outside with my dog, so if you hear some, if I throw the ball, I might just be multitasking while I give this talk. All right, so this is an explosion that we shot on Earth with a really high-speed camera for a TV show I did for National Geographic. Now, it is not a supernova, but, for TV, we have to kind of fake things, and this is as close as we're going to get on Earth. An actual supernova is much, much, much more energetic, and we'll talk about some of the differences in a bit. So why do we do that on TV? Well, let's see. Okay, okay, here we go. Well, in movies and so on, the more explosions you have, the more money you make. So this is real data from Michael Bay movies, and somebody counted up the number of explosions in each movie, and then the amount of money they make. And I had somebody make this graph for a magazine article I wrote, because more explosions, more money. Okay, it doesn't quite work that way in science, but we are discovering lots and lots of explosions. and we're getting maybe more science out instead of more money. So the last supernova in our galaxy seen by humans changed the world, okay? It's been about 400 years. So it was discovered in 1604. And that's called Kepler supernova, because Johannes Kepler made the best observations. He also came up with Kepler's laws, which tell us how our planets go around the sun and so on. And so here's this drawing of the, at that time, they didn't know what it was. They call it a nova, meaning it's something new in the sky. And here's what it looks like today on the right, this expanding cloud of gas, this supernova remnant of what's left over. And how did it change the world? Well, Galileo studied it and lectured on it in Florence. And that's one of the things that showed that the heavens were not perfect and unchanging, as the Catholic Church held. And so, you know, he made some other observations that showed similar things. He didn't invent the telescope, but he helped perfect it and use it for astronomical observations. And so, you know, thanks to his heresy, he was put on trial by the Catholic Church and sentenced to imprisonment, house arrest, basically. And for the 400th anniversary of the supernova, I actually got to go to a conference in Florence, and part of it was held in his house where he was under house arrest, and part of it was held in a lecture hall where he lectured on this supernova that we're still talking about today. So these things are quite profound events. But today, a supernova only occurs in a galaxy about once a century, so we're a little behind, it being 400 years since humans saw one in our galaxy, although there have been ones we missed. So then to study supernovae, I wouldn't have a career unless we had another trick, and that is that we monitor millions of galaxies and look for new explosions. So there are about 30 supernovae discovered per day in distant galaxies, but the problem is they're so far away, they're just a pinprick of light. So here is a zoom in to a galaxy with a supernova that we'll actually talk about a little bit later. This was discovered by an amateur astronomer, a Japanese astronomer. And okay, there's the supernova. It just went off really bright. This will repeat, okay, and then faded. And that's a time lapse over many days. Supernovae generally go up, rise to a peak brightness over a few weeks, and fade again. So maybe a few months to observe the whole phenomenon. Okay, so since they're point sources, we have to use our telescopes, and then we can gather information about them, but it's hard to resolve the individual details of the explosion in terms of like a big explosion like you saw at the beginning. So one way we do gather all of these details is using Las Cumbres Observatory. So this is a network of telescopes we have built all around the world, and they're robotic. So why do we put telescopes around the world? Well, I'll show this actual data from the MESSENGER mission as it flew by Earth on its way to Mercury that shows the Earth rotating. Okay, so we all know this, but look at all those clouds everywhere. Sometimes when you want to take observations, you can't because there are clouds in the way. And the other thing is, of course, that there's a night side and a day side to Earth. So if you have a telescope, if you have a telescope and it's still the daytime, you need to make an observation right now, you might not be able to. But if you put telescopes all over the world, you can have telescopes always have telescopes in the dark. So here's our map of telescopes. We have 23 installed right now. The telescopes, the 1 meter telescopes going to Tenerife got delayed a little bit because of COVID, but they're on their way there right now. And then we're building telescopes to put in Tibet, which would be our last site, and complete the whole network. So there's a ring of telescopes in the south. There will soon be a ring of telescopes in the north. So at any time, if we need to make observations, we can make them, or we can make continuous observations around the clock, which you can't do at a traditional site because you have to stop, pause for the daytime. And of course, telescopes in the north and south are important because you can see only certain parts of the sky from the north or from the south. Okay, I lead a project called the Global Supernova Project, and it's trying to use these telescopes, which are specially designed to discover, well, to understand things like supernovae. And so this is a a good fraction of the worldwide supernova community working together, more than 200 people. And we get the light curves. That means the brightness changes of the supernova, the different color information, and the spectra. That means splitting the light up into a rainbow. We get that stuff for the optical, like what our eyes can see, from our facilities, and then we use other facilities in space and around the globe to maybe look at other wavelengths, for example. So the Hubble Space Telescope, is above the Earth's atmosphere, so it can see some things that we can't. And the same thing goes with NASA Swift satellite and so on. And so we're trying to study about 1,000 supernovae, and we're well on our way to doing that. So why study supernovae? Well, they tell you about stars, how they live and die, and they can tell us about stars in the early universe, where we can't probe from our galaxy because we're looking back in time as we look farther away. They can tell us about the origins of both the elements in the universe and the actual universe itself. Get to that in a little bit. They're laboratories for extreme physics because they can be the birth of black holes or neutron stars, these kind of super extreme things that we cannot probe on Earth because we don't have the capability. You can't build a particle accelerator that can probe black hole energies. And then the unknown, I have put there the James Webb Space Telescope. We've just had our first round of proposals for that. That's going to see farther back into the origins of the universe than we've ever seen. And supernovae can be these like light posts that can light up things along the line of sight there that can probe the early universe. And who knows what we'll find? Maybe the first generation of supernovae even. So just to understand a little bit why supernovae are so important, I'm going to have a slide like this that breaks up different aspects of supernovae we're going to be talking about. At the top, there's a bar that says the relative size of the star blowing up compared to our sun, where 1 m and that little circle and dot, that means 1 solar mass. So where that is, that would be our sun. This is a logarithmic scale, so there's 10 times the mass of the sun and 100 times the mass of the sun. So stars between about a little less than half the mass of the sun and 8 times the mass of the sun will start off like the sun, but then at the end of their life, they puff up and become a red giant star, big fluffy envelope of hydrogen. Then they lose the outer layers and they only leave a core down in the middle. That's material that can't undergo fusion anymore. So it's carbon and oxygen, and that's a white dwarf star. Now, if the white dwarf star is in a binary system with another star and it gains matter, like steals matter from the other star or merges with the other star, it can explode as what we call a type 1a supernova or a thermonuclear supernova. And that's a kind of supernova that doesn't leave any remnant. It just makes a big explosion, but those explosions are fairly standard. Okay, so when that happens, it actually synthesizes elements. So, this is like basically alchemy, right? But it actually, this is why you couldn't do it on Earth. You didn't have ovens that were hot enough. But in a supernova, you have dense conditions of carbon and oxygen that burn, fuse elements to make nickel and so on. And some of the elements you see here, as you go out in the supernova, you get less and less material, less and less dense material. And in fact, the periodic table, the hydrogen and helium were created in the Big Bang, but everything else was created in a stellar or a supernova or a kilonova, as we're going to talk about later. So, as you go up the periodic table, you also need more and more extreme environments. You can synthesize some of the lighter elements in stars, but then you need these extreme conditions of a supernova to synthesize some. So notice all the green there that says exploding massive stars. And then those are a type of supernova we haven't talked about yet, but exploding white dwarfs are in blue there. That's these type of supernovae. Okay, so if you look up your body weight, there's a famous quote by Carl Sagan that says, "We are star stuff." And that's because we are made of oxygen, carbon, hydrogen, nitrogen, these elements that weren't made. Hydrogen was made in the Big Bang, but the other stuff, it took some heavier forge to make this stuff. So if we take those elements and we go to compare it with that last periodic table, it actually turns out that I did this calculation myself, that you are 72% supernova, 18% star, 10% Big Bang. Okay, so maybe we should modify Carl Sagan's quote to "we are supernova stuff." Okay, both star and supernova stuff. So that's one thing that supernovae can tell us about the origins of the elements, but another is the actual origins of the universe and the history of the universe. So these type of supernovae I mentioned are standard candles, so they're about the same brightness. And so if you know that, what their brightness is, you can use them to determine distances. Just like if you had a 100-watt light bulb and you put it far away and you measured its brightness, that could tell you how far away it is. And since light takes a while to get here, the farther back you look, the farther away you look, the farther back in time you're looking. And so when we see the supernovae in these distant galaxies, measure their brightness, determine the distance to them, and then we can also figure out how fast they're moving away from us from the expansion of the universe and build a map of the history of the expansion of the universe. So that tells us how fast the universe is expanding. So in 2011, these guys here got the Nobel Prize. Saul Perlmutter was my ex-boss from Lawrence Berkeley Lab, the Supernova Cosmology project. That's the team he led that I used to be on. And then Brian Schmidt and Adam Rees led a competing team. These supernovae pointed the way towards the universe not just expanding, but getting faster in its expansion, accelerating in its expansion. And since we don't know what was causing that, it requires some kind of energy, but we don't know what it is, so we call it dark energy. It's not the same thing as dark matter, but it's not too, but it's just named that way by analogy. Okay, so that Nobel Prize was awarded in 2011. The work was done a little prior to that, but then other experiments have been done subsequently to figure out what that stuff is. And so that's not really the subject of this talk, but we think the best answer right now is that it's a property of the vacuum of space itself. So I've been part of many collaborations that have tried to figure this out. And so it's what we call Einstein's cosmological constant, we think, but a little bit more on that later. Another thing we can tell from these supernovae is how fast the universe is expanding locally. And that's what we call the Hubble constant. It's just a number that says, how fast is the universe expanding right now today? So the problem that we have right now is that when you measure this quantity, depending on how you make the measurement, you get different answers. Probes from nearby show a Hubble constant of 74 kilometers per second per megaparsec, which, don't worry about the units, that's just a number. But probes from the early universe, well, when you start the construction of them from the early universe, it's complicated, but they give a low Hubble constant of 67 kilometers per second per megaparsec. And these numbers are different by an amount that is incredibly statistically significant if you believe people's error bars. So you can see some of these observations cluster a little high, some a little low, and that's worrisome, let's say. But we recently did some work with Las Cumbres Observatory and some other people calibrating the distance scale slightly differently using a different technique. The ones with the high values tended to be done with Cepheid variable stars, these stars that vary in brightness that allow us to measure distances, to use those to calibrate the supernovae. If we use a different technique, we get this thing in the middle. And so our measurements, most recent ones, are right in the middle, which gives us some hope that it's not new physics what's needed here. That's what a lot of people were saying. Maybe there's something we don't fundamentally understand about dark energy here. Instead, we think there could be something up with the measurements for different groups, some error in the measurements that we don't fully understand, but the jury is still out. We're also trying to do this in a different way with the Hubble Space Telescope, because it can see better in the infrared than you can from the ground. And so we are Every week, we look at new supernova discoveries, and we try to send some to be observed with the Hubble Space Telescope, and then we try to simultaneously observe them from the ground. So there's some measurements we can make better from the ground with Las Cumbres Observatory, some with HST, and we put them together. So when that project is finished, we should have another angle at getting the Hubble constant that will be free from some of the measurement errors that currently plague things like the dust in the universe can mess up your measurements, but with the infrared, you can see through the dust. Okay, and so so the next step to do there in terms of measuring the expansion rate of the universe and getting a real handle on the dark energy, we've done about as well as we can do from the ground, but we need to see even farther into the infrared because that will allow us to see farther away supernovae, and we need to survey big areas of the sky that you can't do with the Hubble Space Telescope. So the Hubble Space Telescope's field of view is like this red square, but with this new facility called the Nancy Grace Roman Telescope, or it used to be called W First, is scheduled for launch in a few years. It's built based on a repurposed spy satellite that never launched, and we will then use it to look at huge areas of the sky in the infrared. And so we took a bunch of data in support of this mission, and that will help tell us, is the dark energy a property of space itself as we think? Is it Einstein's cosmological constant, or is it something different? Okay, so let's move on to a different class of stars, those heavier than about 10 times the mass of the sun, up to about 100 times the mass of the sun. When stars are that massive, they, at the end of their life, become supergiants. So they become really huge. They blow up, balloon up, and they could, if they were at the position of the sun, they would swallow the Earth, they would swallow Mars, and maybe even Jupiter. And when stars are that heavy, they can form elements that are heavier than the carbon and oxygen, like our sun will make in the core. They can burn things all the way up to iron. You can't go farther than that because of basic physics. And then you get heavier and heavier things sitting on the core. The core can't burn and make energy to prop itself up, so it collapses, and you get a black hole or maybe a neutron star, depending on how heavy the star is. Neutron star is just all neutrons. It's like an atomic nucleus, but like 10 miles wide. Okay, it's just it's almost a black hole, but not quite. Okay, so an example of this core collapse of a star that could become a core collapse supernova in the future is Betelgeuse. So if you're familiar with the constellation Orion, the 3 bright blue stars that make up Orion's belt, and then there are 4 stars in a sort of rectangle around it. The top left star underneath Betelgeuse written there, the one that's red, that's Betelgeuse. So this is a storied star from people have known about it for, well, since humans have looked up at the stars, but it could explode. So recently, now Betelgeuse could explode tomorrow, or it could be 10,000 years. We don't really know. But recently, it started getting dimmer, and it does regularly get dimmer, but this was fairly unprecedented dimming, where it was even noticeable to the naked eye. So Betelgeuse is one of those stars so bright it's even hard to measure with professional telescopes, but amateurs sometimes monitor it, and saw this. And right around when that was happening, there was also, from the LIGO project, a burst of gravitational waves. We'll get to those in the future, but that's basically distortions in space-time where, like when, say, 2 black holes merge together, it actually distorts space-time, and it stretches and squeezes space in a wave-like fashion that goes through space, and that can actually go through the Earth and then change distances in the Earth, which we can measure with lasers, and then say over in the sky where that happened. Okay, so back in early 2020, this happened, and I got an alert because I go try to make observations with our telescopes when this stuff happened, and we got a strange detection of a burst, which normally it's a waveform, but this was just a big burst, and that's what's expected when a massive star blows up. Now, I looked at the position of it, and I thought, well, Okay, let me see. Yeah, so I posted something on Twitter, that feeling when you walk outside to check if Betelgeuse is still there. So I just want to make sure it didn't become a supernova, because it had been doing this weird dimming. But it turns out, so here from this article, I quoted one of my tweets where Betelgeuse, wasn't in the localization region, so where the burst came from, but it's right between the two spots where the burst could have come from. But anyway, I wasn't serious thinking that, oh, it's probably Betelgeuse blew up. That would have been too amazing. But I just wanted to just double check on it. Okay. But this did stimulate a lot of interest in Betelgeuse possibly blowing up. So with MESA, which is a stellar evolution code that's publicly available that anybody can use and contribute to, that's developed by Copley Institute for Theoretical Physics here in town. So with some of the students in Lars Bilston's group there at KITP, we calculated the how bright Betelgeuse would be if it exploded as a supernova, and that's in this sort of cyan region. So it would get nearly as bright as the full moon, and it would stay that way for a few months. So, if this does happen in our lifetimes, or whenever it does happen, it's almost like a second moon in the sky for a while, and you'll even be able to see it in the daytime. So everybody around the world will be just totally enthralled by this new thing. Tons more people trying to study astronomy, and tons more people trying to study supernovae. So I kind of hope one of those happens. And that's the only reason that most of you don't know that much about supernovae. If you were living in the time of Kepler or whatever, you'd have been mightily interested in these things because of this. So what was going on with Betelgeuse? Well, here on the left is a simulation. This star is so big and fluffy that it's got this boiling kind of motion where the Earth would just be like, a few pixels in this simulation. So big boiling gas clouds in the atmosphere of Betelgeuse that would dwarf the Earth. And sometimes we think soot forms. And so here are some pictures. Betelgeuse is one of the only stars in the sky where you can actually resolve the disk of it, and it's not a point source. You can actually see it if you use specialized equipment. And so when comparing the data from January of 2019 and December of 2019, you can see half of it sort of looks dark. And so dust actually formed in the atmosphere of Betelgeuse, and that's what we think led to the dimming. Okay, now that's basically forming dust, and it's a mystery where a lot of the dust in the universe comes from. Dust is basically, once you start to put together heavier things than just elements. So it's somewhat like dust in your house, but it's in space. So we have also published papers saying watching dust form in a supernova explosion after it starts to cool. And that's helping to answer some of this mystery of how much there's a ton of dust in the early universe, and we didn't really know where it came from. It seems like dust was forming too early compared to the models and the sites where people thought dust was forming. Okay, so I want to talk about those were the sort of typical types of supernovae, but we've found really exotic new types of supernovae as well. So one is called an electron capture supernova. It happens with stars in between those two I talked about, between 8 and 10 times the mass of the sun. And they have a core made of oxygen, neon, and magnesium. And what happens is, under those conditions, electrons get captured by the neon and magnesium, and it weakens the pressure support of the star, causing it to collapse, and it leaves a neutron star. So that's been a theory for about 40 years, but has never been confirmed. Okay, but people think the Crab Nebula, which is a supernova from 1054 AD that was seen by Chinese astronomers, they saw it visible in the daytime for 23 days, and then at night for 642 nights. And then from figuring out those reports from 1,000 years ago, it was a dim supernova. And then looking at the remnant today, which is what you see in the background there, we think that might have been one of these exotic neutron capture supernovae, but we've never seen one live, that we can actually analyze. And we're not completely sure that's what this was, because without having seen another one, we're relying on these measurements from 1,000 years ago. So we recently got data on this supernova 2018 ZD, and we think it's from one of these electron capture supernovae, where these are supposed to come from, we call SAGB stars, so super asymptotic giant branch stars, which is just a fancy name for they're very big. And they should be rich in helium, carbon, and nitrogen, but poor in oxygen. And the material around the outer layers of the star should get cast off, and the supernova should have a low explosion energy itself, but then run into this material, which will make the energy sort of be larger earlier as these interactions are going on, but then go down and drop off quickly. So it should have a low yield of radioactive elements. And so a graduate student working with me, Daichi Hiramatsu, found this evidence of what we think is the first good case of an electron capture supernova where we saw the supernova actually happen. So he submitted that work to Nature Astronomy, and it's been accepted, but it's still about to be published. And so we'll have a big press release when this comes out, and there'll probably be magazine articles and whatever about it. But this is you're hearing it here first. We're not doing press on it quite yet. Okay, so that could be a whole talk in and of itself, but just to keep moving things along, what happens when we get to stars that are 100 times the mass of the sun, more than 100 times the mass of the sun? There's another theory that we haven't really verified in nature, and that's called a pulsational pair instability supernova, or a pair instability supernova. And that happens when in the core of a star, it gets so hot that according to Einstein's equation, E equals mc squared, we can turn matter into energy and vice versa. Well, if you get so hot, you could actually turn the photons into electrons and positrons. And then they can weaken the pressure support, cause the core to contract, and make a thermonuclear explosion or a series of pulsations, and like sort of mini supernovae over hundreds of years or dozens of years leading up to a final supernova. So that theory dates from the 60s, but had not been confirmed. But a few years ago, we think we may have seen the first evidence of this. So this was another Nature paper by was my postdoc at the time, Yair Akavi. And on the right hand is a sort of schematic of the brightness of the supernova over time. This is going on for a couple of years, which is much longer than a traditional supernova. And instead of one peak, a supernova usually rises to brightness, peak brightness, and falls. This thing had undulations where it kept going up and down at least 5 times. And it was much brighter, as you can see there, than a traditional supernova that's in blue. So, it's billions of times brighter than the sun, and changing in luminosity. And what's more, we think that we looked at old photographic plates, and we saw a supernova at that same position in 1954. So we think that, this was one of these types of supernova that's sort of exploding over and over again, which is hard to understand unless it was one of these pulsational pair instability supernovae, because a supernova should be terminal and just blow itself up unless this kind of craziness was going on. Now, these supernovae were thought to really happen from supernovae from stars in the really early universe, before a lot of the heavier elements were made. But it's possible that one survived. So this is almost like seeing a dinosaur, walking around today, because they should be extinct. And so these are the type of supernovae we hope to find with the James Webb Space Telescope, so we can compare them to this data on something relatively nearby. It was in a tiny galaxy that doesn't have a lot of heavy material. So that's how something could possibly have survived to this day. All right. So next up, we're going to switch gears and talk about After I've exploded this supernova and I've left a neutron star, it's almost a black hole, but not quite. Well, what happens if it's in a binary system with another massive star that explodes, makes another neutron star, and then those two neutron stars merge together? What happens? All right. So this is called a kilonova. And so I have a show called Science versus Cinema, but which we usually talk about science in movies. But we made about a 5-minute video to talk about the discovery of the first kilonova before it was announced to the public, because we were involved in it. And I released this when I was on the stage at the National Press Club, about to go and announce this big thing to the world. And so, like, while I was on the stage, I made this video. While I was about to go up on stage, I made this video public. Doing the first announcement, we made the video partly to document, because we knew this was a historic thing. So I'll play a clip from LIGO, this series of these laser detectors around the world, detected these distortions, and they point us to somewhere in the sky that's in this blue region. So we get a text from them. It can wake you up in the middle of the night. You've been hiking before and got one, at the top, as I was approaching the top of some mountain, and then got some alert saying, "Oh, we've got to make new observations," and so tell everybody, "Oh, we got to go back home right away because the universe is calling." But so when we get one of these alerts, we just freak out. Okay, that's the normal thing, and we start calling all of our friends around the world to try to make observations, or we submit robotic observations to our telescope. So I'll let another little about 1-minute clip where Yair, who again was a postdoc working with me at the time, will tell us what happened.
So we get this alert from LIGO, and then what happens?
Right, so they send us this localization region in the sky, which was about 30 square degrees big, and they say, the event happened somewhere in here, but we don't know exactly where, which is why we had prepared this software in advance that would figure out what galaxies in those 30 square degrees we should be looking at first, based on their mass and distance, and then sends that information to the telescopes, and the telescopes start looking at these galaxies one by one. Lucky for us, galaxy number 5 on our list was the one that had the explosion in it. There were like 5 other groups that were looking at the same galaxy as we were in the same span of 45 minutes. And then we all started sharing our information about what we had seen happen there.
Even satellites in space got in on the action, like NASA's SWIFT satellite and the Hubble Space Telescope. Ground-based telescopes were at a disadvantage though. The explosion was only visible for about an hour at the start of the night. You'd then have to wait 23 hours to see it again from the same telescope. Getting around that limitation is exactly why we built Las Cumbres Observatory. It's a robotic network of telescopes placed all around the globe so that there are always telescopes in the dark. These icons represent where we have telescopes. When we first discovered the explosion, it was over Chile. But then, as the Earth rotated, we picked it up again over Australia. And then, 8 hours later, we saw it over South Africa. In the 24 hours that the Earth takes to rotate, we can observe the explosion 3 times with our network.
All right, so yeah, here's the image of the galaxy on the left before there was the kilonova, and here it is on the right. The kilonova is just this point source there, which we then measure the change in brightness over time and get a spectrum where we split the light up into a rainbow. So there were something like 80 institutions around the world that participated in these kinds of discoveries, including that observed this one area of the sky, and 7 telescopes in space. So everybody on Earth for about at least 4 or 5 days, but then some going on even longer, was trying to observe the same thing. So this is, as I mentioned, so first telescopes in South America picked up the thing, and now this is brightness in millions of suns on the left. And then as the Earth rotated, and our telescopes in Australia saw it increasing in brightness. And then as the Earth rotated, they saw it fading in brightness. And then it was also getting redder over time. Okay, so with a normal facility, you could only take these observations sort of every 1 day. So you would have had 4 observations, and you would have just seen it fading. We were the only people to see it rising before fading, because we could get on it fast, and we could we co-discovered it, and then we could also monitor it faster than other people. Even a lot of telescopes in space can't do that. The Hubble Space Telescope cannot monitor something that rapid. So we can see them. Well, we're working with them though. So in the end, it was about we made a single paper with every author in the world who was studying this. 3,500 authors. Everybody putting some of their data together. We also wrote individual papers. And so on that first day where we announced the results, there was 80 papers announced. And that was only 2 months after the initial discovery, which is just unprecedented to analyze all of that data, totally new phenomenon, write the papers and get them refereed and accepted. So quite a modern miracle where everybody in the world is coming together to come to the same conclusion, or we have our differences on what exactly happened, but pretty much the same conclusion of what happened. So this is the brightness over time, and on the left, less than 1 micron there is the optical part of the spectrum, where what your eyes can see, a little to the blue of that, and then on the right, that's the infrared part of the spectrum. So early on, the first few days, it was very blue, and but then over time, it became more and more dominated by light in the infrared. And we think that's because there were some elements that were created in the kilonova that block out infrared light. And they block out optical light, forcing the light to come out in the infrared. And that's from these lanthanides, these elements on the bottom part of the periodic table that's attached down there. And so some of those and some of the elements not quite that heavy, they're in the orange. That when it says merging neutron stars, we think those elements were created in a kilonova like this that happened, in our neighborhood billions of years ago. So, long before the Earth was formed, some other kilonova happened, and the Earth and the Sun were created out of the ashes of some of that. And so, this is where now we think gold and platinum and things like that, the heaviest elements, come from. So if you have gold jewelry, it was created in the creation of a black hole as 2 neutron stars merge together. And LIGO is revolutionizing our understanding of black holes. Here's a chart of some of the massive black holes that we have seen. We didn't know about this before because we couldn't sense 2 black holes merging together because it doesn't produce light in a normal case. But we can now sense the distortions in space-time. And so it's, aside from just the merger of 2 neutron stars to make a black hole, that's what's down at the bottom there. We're now actually seeing black holes merge together as well. And so this is another case where modeling this is telling us something about how supernovae explode, and supernovae are telling us something about black holes, how black holes are created, and then ultimately how they get together and grow in size up to millions or billions of times the mass of the sun. The kind of thing we see at the center of every galaxy, which is one of the most outstanding questions in astronomy today. we don't know the guess too. Okay, so that's it for the science part. But next, I want to talk a little bit about science communication. And so when I go and give talks about science, but usually you get the people who are already interested in science. They're the ones that want to hear it. But a lot more people watch shows, entertainment and movies, and that's how a lot of people get their scientific knowledge or misconceptions in the first place. So I have a show on YouTube called Science for Cinema, where I talk to people who are doing the science in a movie and say, did they get it right or not? Sometimes they're the science advisor, sometimes they're just other people doing the same science. And then I also talk to the actors and directors and people who made the movie about what were they thinking in the way that they approached science. Did they do their homework or not? So I'll play this clip from our episode about The Martian.
Of course they shot The Martian on Earth, but Martian gravity is only 38% of Earth's gravity. To see what that would look like, I got on a gravity treadmill. All right, so this thing is inflating my pants. It has to lift me off the treadmill, basically. You just kind of really jump up in the air with every step. Basically, you can jump higher, and even walking would look different. Why didn't they try to show that in The Martian? I asked Ridley Scott.
Did you talk about trying to portray more Mars gravity?
Are you an expert?
How much do you know?
I'm an astrophysicist.
Earth's gravity, Mars is 40%, right, of Earth. So by the time you put on a fairly chunky suit, it's fairly heavy. So we worked out the mathematics roughly. It's kind of more or less just under norm movement. So that's where we made a decision. So we were wrong, right?
We're not at the point where we can do 40% gravity. I mean, we can do weightless.
We see Mark Watney walking around without a suit, and it still looks like he's on Earth. So the real answer is, it was just too hard to shoot. But imagine how much more immersive the film would have been with that little touch. While we're on the subject of spacesuits, are those slim fit suits realistic? Not really. Even on Mars, you need a puffy, pressurized suit and a backpack with breathable oxygen and climate control. Matt Damon should have been a little lighter on his feet, even in his suit.
Yes!
On the subject of gravity, I really wish Ridley Scott would have gone that extra mile.
All right, but otherwise, The Martian is pretty good. And Andy Weir, who wrote the book, does an excellent job of doing his research. And I did a little bit of science advising for his next book called Project Hail Mary that should be out in a few weeks now. So should be fun to check out. All right, and just another little clip on the movie Arrival, which is basically about, I won't give away the real spoilers, but it's if aliens came to Earth, how would we communicate with them? And what would that teach us about ourselves? And so one of the people that was the science advisor on the movie was Jessica Kuhn, who's a linguist. And so I'll let her take it from here.
I was asked to read drafts of the screenplay and give feedback on the more linguistically relevant parts. They took pictures of my office. They wanted to know, what kind of bag do you carry?
Pack your bags.
Oh, you've got a tea kettle. Okay, good. She's going to have a tea kettle. And then I got to have lunch with Amy Adams. And that was a lot of fun. Also, she had lots of really good questions about, what's academia like? What's it like to be a woman in academia? What's it like to do field work?
What was wonderful and what kind of freed me up to play this was that I asked her how many languages she spoke, and she's like, it's funny, that's what everyone thinks, that we're like interpreters or translators.
There's one part that I think is going to make every linguist cringe, and it's in the trailer, and it's when Forrest Whitaker comes into her office and, plops down the recorder and says,
"You're at the top of everyone's list when it comes to translations."
As linguists, we really have to fight against this misconception that we are just glorified translators, right? That we just speak a lot of languages and that we're just learning languages, because really we're learning about languages and studying the structures of them.
It was also helpful because she's a very warm woman, and there was something about her that it kind of reminded me of Louise.
But they were very kind and very gentle when they explained to me that, you know, theoretical linguists are really not Hollywood's main audience concern.
All right. So that's it. But just to conclude, we're in this incredible age of supernova research where we have new facilities to be able to see the sky in a new way. And so as a result, we're able to find out totally new things about stellar evolution, the origin of elements, the origin of the universe for the first time. And so some of that is because we have space facilities, and some of that is because we have new technology that we're building here in Santa Barbara and putting around the world. And so, yeah, particle physics, black holes. I mean, there's so many other things I didn't have a chance to talk about because we just ran out of time. But we also work with detectors in Antarctica that detect neutrinos and try to look for supernovae associated with them, with other things called fast radio bursts, and try to look for explosions associated with that. All kinds of new phenomena are being discovered in astrophysics. So here is a picture of Einstein when he was visiting Santa Barbara, looking out and thinking deep thoughts about the universe. You know, but you can tell he's from the East Coast because here he is wearing a suit at the beach. Okay, but anyway, sometimes when I get out of the beach over there, I try to think deep thoughts as well about what are we learning that he would have really appreciated if he were around today, to see all of the exciting new discoveries that we're making. So that's it, and I'll take questions.
Great. Does anyone have questions? I had one, and that's with the supernova, the kilonova that occurred. It was sort of off axis from the center of the galaxy. And so if a supernova in another galaxy occurred and it was near the center, would we be able to see it?
Yeah, that's a good question. So basically, galaxies can be obscured by supernovae can be obscured if they're buried in dust in the galaxy, or if they're the center of galaxy where there's a lot of light. Especially if that's an active galaxy, one whose brightness is changing rapidly. And so there are certain kinds of searches for supernovae that look for supernovae that might be obscured. So you can look in the infrared to get through some of the dust, or if you have a good census of all of the active galaxies, you can help rule some of that out. But there are some new phenomena that are at the centers of galaxies called tidal disruption events that we also study. And Yair Akavi, who was in the video, who was a postdoc here, who's now a professor at Tel Aviv, he's one of the world's experts in those. And they are when a star gets ripped apart by a black hole, and it creates this increase in brightness and decrease over a few months that looks a lot like a supernova. But it can also look a lot like an active galaxy when a black hole is accreting material. So it's one of these cases where the ambiguity can be serious, and sometimes we just can't figure out if this is a star that's got ripped apart by a black hole or just some other material that's being eaten by the black hole. But it's an exciting new area of research because we only just started learning about these a few years ago, we're still in the early phases of putting together the sort of full catalog of what these things look like and what all their properties are. And again, it's where you got to pair things with X-ray observations from space, because the X-rays are like an ultraviolet and gamma rays are the highest energy photons. And those come from, things near a black hole are often going to be very high energy. And so you need to pair those space-based and ground-based facilities together.
Cool. Other people have questions? Go ahead and speak up.
Andy, does a gravitational wave move faster than other sorts of distortions in space?
Yes, that's a good question. And we think that as far as we can tell, the gravitational waves move at the speed of light. So there was a difference of 2 seconds between the arrival of the gravitational waves and the gamma rays from the kilonova. And we think that's because it actually took a while for the jet to punch out of the star, but we're not completely sure. But anyway, that sets a constraint, and that's, remember, 2 seconds over millions of 100 million, 120 million years it would have taken the light to get to us from that explosion. 130 million, I think. So that's quite an incredible constraint on the speed of gravitational waves.
Hi, I'm a student at Thatcher. Can you hear me?
Yes. Hello.
Hi, I'm Cyrus. I'm a student at Thatcher. So my question is, can LIGO help with supernovae detections?
Can LIGO help with supernovae detections? Well, if there is a burst from LIGO, that one that we found earlier turned out not to be related to Betelgeuse, but in principle that can happen. And if that does happen, yes, we can, for a very nearby supernova, like one in our galaxy, we might get the first detection of it from LIGO. It would also produce neutrinos, and there are some neutrino detectors that also might help us get the first detection, get a heads up for things in our galaxy. It can then take hours for the shock of the supernova. So that is information from the core of the star that gets immediately communicated to us, because the gravitational waves can get out of the star, and the neutrinos can as well. They pretty much fly through the star. But the star is so dense that the photons actually take a while to get out, and so it can take them, this sort of, it can take a while for the shock to get out of the surface of the star, and it will, so there can be a delay there. So, and it can actually take a little bit of time for the brightness of the star to get large, because it basically has to do with the high energy photons and then how they convert into optical. It's a little complicated, but basically it can take a while for the radioactive material and the shock and everything else to deposit its energy and cool down, and this whole set of processes. So, but for distant supernovae, we pretty much see the optical light first, because they're too far away to see the neutrinos and the gravitational waves. So we can only use that for relatively nearby cases. For these merging neutron stars, those were in a distant galaxy, but they were still a relatively close by galaxy, 130 million light years away. But the merging of two black holes or neutron stars is much more energetic in a way of distorting space-time than a single star collapsing, and it has to do with the shape of the explosion. So there's some hope, but for the vast majority of supernovae, our gravitational wave detectors aren't sensitive to detect them. I see another question here on what would you be looking to measure in order to determine what dark energy is? Yeah, it's a good question, and the answer is we want to find more of these standard candles, these type 1a supernovae that are out there very far away in space. And we actually have good measurements moderately far away in space. I mean, I'm talking about billions of light years away, up to maybe 10 billion light years away. And so, some of those supernovae happened before the Earth was here. The photons have been going through space ever since. But what we want to find is more supernovae nearby. And ironically, those are harder to find, because instead of just looking deep with one telescope and staring at one little part of the sky and sort of taking a core sample of the universe, if you like, you find a lot of supernovae, because that's a lot of volume. To do the same volume locally, you don't have that depth, so you have to just look all over the sky, and that's harder to do, to monitor the whole sky for supernovae. So we need more supernovae locally. That's one reason why we're getting a lot of the key data from our observatory here. And then we also need data even farther away, and that's why we're building this, Nancy Grace Roman telescope. There, you need to look in the infrared, because the light is redshifted by the expansion of the universe, so the photons are stretched out. They become redder and redder, and that means we need these big, huge detectors in the infrared, and those are only just now becoming available, like technologically speaking. And so that's why we haven't been able to see that far yet, but with this new satellite, we'll be able to. So just more supernovae and at different places than we've seen them before. And that helps us make the map of the expansion better, because we need to see if the expansion rate of the universe is changing over time. So if you like, we know sort of how it's been going in the middle of the universe, but we need to see, is it changed very, very recently, and how was it different at the very early days of the universe? How many scientists were discovered in the discovery of the, how many scientists were involved in the discovery of the kilonova? So there's two parts to this. One is the discovery, and then the other is the characterization of it. For the discovery, there were 6 teams that all discovered this. They took the first images of the supernova within 42 minutes of each other. And that's because that's the only amount of time it was visible, because it was close to the sun. So you could observe it like right before the sun set, but then, you know, you couldn't see it anymore because the sun, it was just after the sunset, but then the object set. And so you couldn't see it anymore. And so you're trying to make these difficult observations. And 6 of the groups, so my group was one of them, and there were about, I don't know what, in the group that, in our group, there were about 12 people or something like that. But some of the other groups might have been, you know, of order that maybe, we were one of the smaller groups, so some of the others are like 20 people or something like that. So maybe, you know, of order 100 people, or I don't know, 50 to 100 people in the discovery part of it. But then in terms of characterizing the supernova, once everybody announced the results, that, hey, it's out there, which we did kind of in a secret forum, because since it's the first time this detector was being used in this way, they made everybody sign a secrecy agreement that said basically, we're not going to tell the press or whatever about this until we study it and determine what's all going on. And then we're going to announce the results all at once, because it's a new technology and they wanted to make sure that everybody's doing everything right. So 3,500 people were involved in that whole bigger study. And that includes some of these people building and maintaining the LIGO detectors. I think there's something like 900 people doing that. There's a similar number of people doing the ice cube detectors, which did not find neutrinos, but this is this detector in Antarctica. And but we used their limits to, you know, say something in the first paper on it. So yeah, a lot of people in the world, but also at the same time trying to keep a secret. And it did leak a little bit. Some reporters found out about it a little early. So this is when people are talking about conspiracy theories, you know, like, oh, NASA's hiding aliens and all this stuff. I can tell you that's quite hard to do if a lot of people know the secret. Okay, another question from the chat here is, let's see, are there supernova candidates you're watching other than Betelgeuse? Yeah, so one thing is, for the vast majority of for almost every supernova, and I mean like almost every, we don't have any indication that something is going to explode, because they're very far away galaxies, and we can't resolve the individual stars in the galaxy. So we don't know which one is going to blow up. So we just see the explosion after it's already started to happen. And it's only for the things in our galaxy, or very, very nearby galaxies, that we can say, oh, that star looks like it's having problems. And so we haven't seen that where a normal star like Betelgeuse, say, just blows up. But what we have seen is these things called luminous blue variables. And those are very massive stars that are having some kind of big, huge explosions or pulsations near the end of their lives. And they're having almost like a little mini supernova, and it's throwing off the outer layers. The star Eta Carina, which is in the southern hemisphere, is one of these kinds of stars, and it had a big outburst in the mid 1800s. And people didn't have telescopes at the time to see that eruption. We can see the after effects now with the Hubble Space Telescope. You can actually resolve that, but we've actually been able to observe the light echoes from that with Las Cumbres Observatory. And that is when the light, some of that light from the mid 1800s went the opposite direction from Earth, and then bounced off a gas cloud, and then is now coming back to Earth, just like a sound echo, but with light. And using that information, we can reobserve the great eruption from the 1800s and learn a lot more about that process, which is pretty rare. But we've now seen a few cases where a supernova, a star that people were monitoring because it was a luminous blue variable, then later exploded. And we don't know, we can't, so people are monitoring lots of luminous blue variables. We don't know which ones are going to explode and when. And that's not your typical supernova, but that's happened a few times, which is very exciting. Okay, another question is, what does LCO look for as ideal locations for satellites? Are there challenges to securing desired placement? Is negotiation and location of satellite ownership of data a matter of international diplomacy? Yeah, so instead of satellites there, I would say telescopes. So when it's on the Earth, we call it a telescope, and in space, then we call it a satellite. But yes, so you want to, there are a few conditions you want one where it's a dark sky, where the weather is good pretty much year round, where it's the atmosphere is relatively still, because if the atmosphere is turbulent, it can smear out our images. That's why stars twinkle. If you get too much of that, it messes up your observations. And so you also want a smooth airflow that helps with that process. So you want mountains in general, because that gets you above most of the Earth's water vapor, which also causes problems. And you want a smooth airflow over those mountains. So you want gently sloping mountains. You want to be away from a lot of light. So that basically means islands are good. So that's when volcanic islands, especially like Hawaii, which has these gently sloping mountains. So that's the best spot on the planet is Hawaii. Chile is also the best spot in the Southern Hemisphere. Those locations in the Canary Islands were another good one. And it helps to have pre-existing infrastructure where there are other telescopes, and then data, like people put monitoring telescopes at a potential new site and let them sit there for years and gather data. And so now with our network, we want to have them spaced all around the globe relatively equally. So that means there's only 3 obvious spots to put them in the Southern Hemisphere, where the continents dip down, and that's where we have telescopes. Now in the Northern Hemisphere, there's a little bit more options. You need Hawaii, of course. But then there's, stuff in North America. So we put stuff in Texas, but then there's, that leaves the sort of Asia region. And so, yes, this Tibet, China, there are, political issues there, but the issue is almost everywhere else there are monsoons, and or there's not mountains high enough, or there's not pre-existing infrastructure. And so it's one of the only possibilities left. So then we just have to deal with the politics of it. And, the Chinese government may or may not allow you access to the site in the right way you want, or there's, but, we have good, we work with a lot of Chinese colleagues around the world. They're in my project, the Global Supernova Project. When it comes to the scientists, we work fairly well together. Politics doesn't come into it too much, but it's something to be aware of. Could a telescope be built on a platform in the ocean, like platforms off of our coast? In principle, yes. Although to keep things stable, we put a pier that goes down into the earth. That's even so that like a building with a telescope around it. I mean, a telescope in a building, you don't want wind hitting the walls of the building or people walking around even in the building to affect their vibrations can affect the telescope. So you would probably not want to have a thing that was just floating on the ocean. You would need to really drill down deep. And so that makes it probably prohibitively expensive. And of course, you need infrastructure for a telescope. You need people living there. You need easy access to get there, unless it's a robotic facility. But even then, you need people to be able to go and fix it, work on it. So it's a matter of expense there, I think I hear somebody's microphone that might want to mute if you're not talking. Okay, so let's see. Other questions?
Do other people have questions they'd like to ask? Okay.
Yes. How's recent space travel like to Mars helped with your observations? So pretty much all of our observations are made by either satellites in low Earth orbit or telescopes on the ground. So you don't need to go far away. So, the Hubble Space Telescope is in low Earth orbit, but it can just see really far away. So that's so there's always this division between NASA, between the human spaceflight side of things and the scientific side of things. And so NASA works best when there's a sort of wall between those, where it's not like, okay, if we spend more money on human flight, we're taking money away from the science side. But I'm a big fan of both. And the Mars rovers are an incredible technological achievement. It would be great if we could have, for example, telescopes one day on the moon. On the far side of the moon is a really radio quiet place. You could build a huge radio telescope in one of the craters there. But that's an engineering challenge, and that's decades away. But it would be cool to make some observations like that. Now, we have done observations with distant satellites. In a few cases, there's the New Horizons probe that is gone beyond now Pluto. That's the one that made the observations of Pluto. It's going so fast that it couldn't even stop at Pluto, and it just had to keep going. So it's well beyond Pluto at this point. Las Cumbres Observatory made observations in conjunction with that satellite of the parallax of stars, and that's that we see the positions of stars change as the Earth moves around the sun, or if you just have two vantage points. So it's like if you put your finger out in front of your eye and you blink, you'll see your finger move relative to background objects. That's parallax, because you're looking from two different vantage points, and you can use that to determine distances. So if you see a star, so nearby stars will move relative to background stars if you're looking from two different vantage points, and you can determine a distance to a star. So if we can take our facility and observe at the same time that this satellite is observing, then we could make special observations that nobody's been able to make before. And similarly, those kinds of probes can see things that are blocked by the sun, because it's at a different vantage point in the solar system. So occasionally astronomers will use different facilities to, like, say, triangulate some arrival of gamma rays or make some other observation that's hard to, just because of our limited platform on the Earth. Okay, how much trouble are the new communication satellites causing for your work? Well, a lot. So what this is referring to are these Starlink satellites that are being put up by SpaceX, Elon Musk's company, and it's a constellation of satellites. So they're trying to put up 12,000 satellites, and to provide Wi-Fi coverage for people. And then Amazon has a constellation of satellites they're putting up as well, and there's another company called OneWeb. And the problem is they can be seen at visible wavelengths. So, and with your eye, they're brighter than 6th magnitude usually. And so you can see them in the night sky. Now, there's about 9,000 stars or something you can see in the night sky. Put 12,000 of these up, these are going to outnumber stars in the night sky. So at dusk and dawn, when the sun is still glinting off the satellite, though it is set from our vantage point on Earth, you can see these things. And then even if they can make them such that you can't quite see them with your eyes, which they're working on, we can see them with our telescopes. And so they mess up observations. They make these streaks in our observations. So we are talking with the Starlink and SpaceX people about mitigating the threat, trying to paint them in certain ways, trying to make sure they're oriented in certain ways, and then trying to locate all of their positions and put them in a database, and so that astronomers can change their observations so that they don't get ruined by these things. But it's a difficult question, and it wasn't thought about ahead of time. And it's one of these cases where this is a sort of global commons, the night sky, and it's like a heritage of all of humanity, but people can use it to just profit off of without paying costs associated with that. And that's really the only reason these things are economically viable, is because they're not paying the true cost of what they're doing. It's similar to global warming and things like where if you can just pollute, then people will do it without having some kind of consequence. So we're trying to do the best we can with what we have, but the regulations and or willingness to regulate, or companies even willing to follow the regulations. There are some regulations in some cases, and the companies have just refused to follow them, and there are no consequences. So it's very frustrating as an astronomer.
Other questions? Can you tell us anything more about this Andy Weir movie coming up? I hadn't heard about it yet.
This is just a book. This is at this point, but I think it's been optioned for a movie. It's called Project Hail Mary. I am sworn to secrecy about what the plot is, but I think it's a really cool idea, as long as, I haven't read the final version yet, but from the bits of the story that he told me to ask questions about it is very, very cool. So look for that. But if you haven't seen I haven't read his second book, Artemis.
Oh, that's a great
also
book.
Yeah, it's also really good. So that's, I think, been optioned for a movie as well. I don't know what stage of development that's in, but yeah, he's one of those guys that writes a lot of cool stuff, and I'm going to read whatever he writes for sure.
Other questions? Thank you so much for the presentation, Andy. Really appreciated it.
Thanks for having me.